You have survived every thunderstorm you've ever been in. Every single one. If you're an average American, that's several hundred over your lifetime backyard barbecues, kids' soccer games, lawns half mowed, a weather alert glanced at and dismissed because the storm was still pretty far out. That perfect survival record is not evidence that you understand thunderstorms. It's the reason most people don't. Lightning kills more Americans most years than tornadoes do. Flash flooding kills more than both combined. Neither one requires the storm to be overhead or even visible. By the time it reaches you, the National Weather Service has documented hundreds of cases of lightning striking people more than 10 miles from the nearest rainfall, under a clear blue sky. With nothing but a distant rumble, most people don't even register as a warning. This video is about the most common piece of severe weather in the country. Something nearly every American has lived through dozens of times without thinking twice, and the 4 specific, well-documented ways that familiarity is quietly working against you. That clear sky lightning strike has a name. Meteorologists call it a bolt from the blue, and it's a predictable, well-understood consequence of how a thunderstorm's electrical structure actually extends across the sky, not a freak anomaly. We'll get to exactly how it works. First, the scale of what you're dealing with every single summer. The United States experiences an estimated 100,000 thunderstorms every year, roughly 274 per day on average across the country, making it one of the most thunderstorm-prone nations on Earth, driven by the specific combination of warm, moist Gulf of Mexico air colliding with cooler continental air masses across the central and southeastern states. Of those 100,000 annual thunderstorms, the National Weather Service classifies only a small fraction, typically around 10%, as severe, a formal meteorological designation with a specific, narrow definition: a thunderstorm producing wind gusts of 58 miles per hour or greater, hail 1 inch in diameter or larger, or a tornado. This definition matters enormously for how this video is structured, because it excludes 2 of the 4 mechanisms that actually kill the most people in thunderstorms every year. Lightning is not part of the severe thunderstorm criteria. Flash flooding from heavy rainfall is not part of the severe thunderstorm criteria. A thunderstorm can produce lethal lightning and catastrophic flash flooding while never qualifying, by official definition, as severe a gap in the warning framework that this video's twist section will examine directly. In this video, we'll cover 3 things: the actual internal structure of a thunderstorm cell, and how that single structure generates 4 distinct and independently lethal hazards. The specific mechanisms: wind, lightning, flash flooding, and hail through which thunderstorms kill or injure people every year in the United States. And the twist, the structural gap, and how thunderstorm danger is officially classified, and what that gap means for how seriously the public takes a storm that the Weather Service hasn't called severe. We start with the cell itself. To understand why a single thunderstorm can produce 4 genuinely different hazards, you need to understand the basic internal structure of a mature thunderstorm cell. A structure built around 2 opposing columns of air moving in opposite directions within the same storm. A thunderstorm forms when warm, moist air near the ground rises rapidly, the updraft carrying water vapor upward until it cools, condenses, and forms the towering cumulonimbus cloud that defines a thunderstorm's appearance. As the storm matures, precipitation begins falling through this rising air, and the friction and evaporative cooling of that falling rain and hail creates a second, opposing column, the downdraft, a column of rapidly descending air and precipitation that can reach the ground with tremendous force. The first hazard mechanism, straight-line wind, comes directly from this downdraft. When a downdraft reaches the ground, it has nowhere to go but outward, spreading horizontally in all directions from the point of impact, in a pattern meteorologists call a gust front. Under specific conditions, typically involving very dry air at mid-levels of the atmosphere that intensifies evaporative cooling within the downdraft, this descending column can become a concentrated, intense downburst, and at the most extreme end, a microburst, a downdraft so concentrated and so intense that it produces straight-line winds exceeding 100 miles per hour across a localized area, often less than 4 kilometers wide. This is the detail that surprises most people. A severe microburst can produce wind speeds and damage patterns comparable to or exceeding an EF1 or even EF2 tornado. But because the damage occurs in a straight line pattern, trees and structures falling in the same direction, rather than the chaotic, multi-directional damage pattern of a tornado vortex, and because there is no rotating funnel cloud to capture public attention, microbursts receive a fraction of the warning urgency and public alarm that tornadoes receive. Despite causing comparable wind damage and, particularly to aircraft during takeoff and landing, comparable lethality. A visible signature of the gust front mechanism that many people have seen without recognizing its significance is the shelf cloud, a low, horizontal, wedge-shaped cloud formation that often precedes a thunderstorm's arrival by several minutes, marking the leading edge of the outflow boundary where the storm's cool downdraft air is wedging beneath the warmer air ahead of it. The arrival of a shelf cloud is frequently the first physical signal that a damaging wind event is imminent. Often before any rain has begun falling at a given location, a useful, visually distinctive warning sign that most people have observed during a storm's approach without understanding what it specifically indicates about the wind hazard arriving in the next several minutes. The second hazard mechanism, lightning, operates through an entirely separate physical process within the same storm, the separation of electrical charge within the cloud. Driven by collisions between ice crystals and graupel, soft hail carried by the storm's internal turbulence. This charge separation creates regions of strong positive and negative charge within the cloud and on the ground beneath it. And when the resulting electric field becomes strong enough, it discharges as lightning, a channel of superheated, ionized air carrying enormous electrical current between cloud and ground, or between different parts of the cloud itself. The critical detail explaining the bolt from the blue phenomenon involves the geometry of a mature thunderstorm's anvil cloud, the flat, spreading cloud top that extends outward from the main storm tower, sometimes for tens of kilometers, carried by upper-level winds well beyond the area of the storm producing visible rain. Lightning can originate from the charged regions of this anvil cloud and travel laterally before striking the ground at a point far removed from the storm's core, meaning a person standing under clear sky, with no rain falling and the storm itself visually distant, can be standing directly beneath the electrically active extension of a storm they don't realize is connected to them at all. The third hazard mechanism, flash flooding, results not from any single storm's intensity, but from a meteorological pattern called training, in which successive thunderstorm cells move repeatedly over the same geographic area, each one dropping additional rainfall on ground and waterways already saturated or overwhelmed by the previous cells. A single thunderstorm cell might drop a manageable amount of rain in isolation. 10 cells training over the same valley in sequence can produce the same flash flood dynamics covered in our earlier video on this hazard, driven entirely by ordinary thunderstorms that individually would never be classified as extreme. The fourth hazard mechanism, hail, forms when the storm's updraft is strong enough to suspend forming ice particles within the freezing upper levels of the cloud for an extended period, allowing successive layers of ice to accumulate as the hailstone is repeatedly carried upward and recirculated before finally falling once it becomes too heavy for the updraft to support. The strength of a storm's updraft directly determines the maximum hail size it can produce, which is why golf ball or baseball-sized hail specifically indicates an unusually powerful updraft, and why hail size is one of only 2 criteria the National Weather Service uses to define severe. What unifies all 4 mechanisms is that they emerge from the same basic thunderstorm structure, the updraft, the downdraft, and the charge separation driven by their interaction, meaning a single storm cell, classified by a single set of radar and satellite observations, is simultaneously capable of producing damaging straight-line winds, lethal lightning strikes kilometers from its visible core, flash flooding through repeated training, and damaging hail, in any combination, depending on the specific atmospheric conditions feeding that storm. The National Weather Service maintains detailed annual fatality statistics across weather hazard categories, and the data reveals a pattern that runs directly counter to public risk perception, lightning and flash flooding, both thunderstorm byproducts that fall outside the official severe thunderstorm criteria, kill more Americans in most years than tornadoes. The hazard that receives dramatically more media coverage, public anxiety, and warning system urgency. Lightning kills an average of approximately 20 to 30 people in the United States annually. In recent decades, a figure that has actually declined substantially since the mid-20th century due to improved public awareness campaigns. But that remains a persistent, predictable toll. The National Weather Service's lightning safety data shows that the majority of lightning fatalities occur not during the most visually dramatic phase of a storm, but in the moments before a storm visibly arrives or after it appears to have passed precisely the bolt from the blue window this video's mechanism section described. For every fatality, the data suggests roughly 9 additional people survive a lightning strike with significant injury, often involving long-term neurological, cardiac, or musculoskeletal effects. A population of survivors whose lasting health consequences receive far less public attention than the fatality count alone suggests they should. Flash flooding, driven substantially by the thunderstorm training mechanism, has killed an average of more than 80 Americans annually over the past 3 decades, according to NOAA records, making it, in most years, the deadliest weather-related hazard in the United States, exceeding the combined toll of tornadoes and hurricanes in many years. The overwhelming majority of these deaths occur in vehicles, when drivers attempt to cross flooded roadways, underscoring that the flash flood hazard from thunderstorms kills primarily through human decision-making in the moment, rather than through any inability to detect the hazard in advance. The July 2022 flash flooding in eastern Kentucky, produced by thunderstorms that repeatedly stalled and trained over the same mountainous terrain across several days, killed dozens of people and destroyed thousands of homes, a directly documented modern instance of the exact training mechanism this video described, occurring in steep valley terrain that concentrated runoff from a sequence of individually ordinary thunderstorm cells into a catastrophic flood. The microburst and downburst hazard has a documented and specifically severe history in aviation, where the sudden, intense wind shear these phenomena produce has been directly implicated in multiple fatal commercial airline crashes during the 1970s and 1980s. Before the aviation industry developed specific wind shear detection technology and direct response, Delta Airlines Flight 191 in 1985, which crashed on approach to Dallas-Fort Worth Airport after encountering a microburst, killed 137 people, and became one of the pivotal events leading to the FAA's mandatory installation of wind shear detection systems on commercial aircraft and at major airports, a direct documented case of aviation safety engineering responding specifically to the microburst mechanism this video's mechanism section described. Ground-level microburst and downburst damage, while less dramatically documented than the aviation cases, is tracked by NOAA's Storm Prediction Center alongside tornado damage reports. And the agency's data shows that a meaningful fraction of wind damage reports nationally, including instances of significant structural damage and tree destruction comparable to weak tornadoes, are ultimately attributed to straight-line wind events rather than tornadoes. A distinction often only confirmed after a National Weather Service damage survey examines the pattern of fallen trees and debris. The hail damage record is documented primarily through insurance industry data rather than fatality statistics, since hail rarely kills directly but produces enormous property damage. NOAA and insurance industry estimates place annual hail damage costs in the United States at several $billion in a typical year, with severe hail events in Texas, Colorado, and other plain states regularly producing damage in the hundreds of millions of dollars from a single storm system. Here is the detail about thunderstorm risk communication that most Americans have never had explained to them directly. Despite having heard the phrase severe thunderstorm warning announced on their phones dozens of times, the official criteria for that warning category include only 2 of the 4 hazard mechanisms this video has covered. A severe thunderstorm warning, in the formal National Weather Service definition, is issued when a storm is producing or expected to produce wind gusts of 58 miles per hour or greater, hail of 1 inch in diameter or greater, or both. That is the complete criteria. Lightning intensity, lightning frequency, and flash flood potential are not part of the severe thunderstorm warning decision at all. They are handled through entirely separate warning products, including flash flood warnings and general public lightning safety guidance that doesn't carry the same alerting mechanism as a severe thunderstorm warning. This means a thunderstorm can be producing the single most lethal mechanism this video has documented. Lightning capable of striking 16 kilometers from the storm's core, or rainfall intensity capable of producing flash flooding while never triggering a severe thunderstorm warning at all, because its wind speed and hail size remain below the formal threshold. From a public risk perception standpoint, this creates a systematic and somewhat counterintuitive mismatch. Storms that get the most urgent warning label are not reliably the storms producing the deadliest hazard mechanisms in any given instance. This isn't a flaw in the warning system so much as a reflection of how the warning system evolved historically. The severe thunderstorm warning criteria were established primarily around wind and hail, because those were the mechanisms most directly tied to property damage assessment and the most straightforward to verify through radar and damage surveys. In an era when lightning and flash flood risk communication developed along separate, specialized tracks within the Weather Service's broader hazard communication framework, the result, however structurally explicable, is a genuine gap the warning label most familiar to the public, and most associated in public perception with "this storm is dangerous," does not reliably correlate with the storm's most lethal potential. The practical consequence of this gap shows up directly in the fatality data. This video's evidence section presented lightning and flash flooding. The two hazards excluded from severe thunderstorm warning criteria are responsible for more annual fatalities than tornadoes, the hazard most closely associated in public consciousness with thunderstorm danger. People reasonably calibrate their behavior to the warning labels they're given when a storm doesn't trigger a severe thunderstorm warning. Many people correctly infer that the wind and hail risk is low, but may incorrectly infer that the storm overall poses limited danger, missing the lightning and flash flood risk that the warning category was never designed to communicate in the first place. The geographic distribution of thunderstorm risk across the United States reflects the specific atmospheric ingredients this video's mechanism section described. Concentrated most intensely in regions where warm, moist air masses regularly collide with the conditions needed to trigger and sustain severe convection. Florida experiences more thunderstorm days annually than any other state. Central Florida, particularly the Tampa Bay region, is sometimes called the lightning capital of North America, driven by the daily sea breeze convergence pattern created by the Atlantic and Gulf coastlines meeting in the peninsula's interior, producing thunderstorms on the majority of summer afternoons. This geographic concentration translates directly into Florida's consistently high lightning fatality statistics relative to other states. The broader Tornado Alley region across the Central Plains, Texas, Oklahoma, Kansas, Nebraska experiences the conditions for the most intense severe thunderstorms in the country, including the supercell thunderstorms capable of producing the largest hail, the most violent straight-line wind events, and the tornadoes covered in this series' earlier video. The Dixie Alley region across the Mid-South and Southeast experiences a related but distinct severe thunderstorm climatology, with storms often occurring overnight and in cooler months. A pattern that has been specifically associated with elevated fatality rates because nighttime severe weather catches sleeping populations with less warning time to respond. The economic scale of thunderstorm-related damage in the United States, aggregating wind, hail, lightning, and flash flood losses, runs into tens of billions of dollars annually according to NOAA's billion-dollar weather disaster tracking, which counts severe thunderstorm events as a distinct and consistently significant category alongside hurricanes and wildfires. Severe thunderstorm and hail damage has, in several recent years, exceeded the combined cost of U.S. tornado damage, reflecting both the broader geographic footprint of thunderstorm events and the sheer frequency with which they occur compared to the much rarer tornado. The derecho, a long-lived, fast-moving line of severe thunderstorms, producing widespread straight-line wind damage along a path of at least 400 kilometers, represents the most extreme expression of the wind mechanism this video's mechanism section described, scaled up from an individual microburst to a continental weather system. The August 2020 Midwest derecho, which tracked from eastern Nebraska through Iowa, Illinois, and Indiana in a matter of hours, produced wind gusts exceeding 100 miles per hour in some areas, destroyed an estimated one-third of Iowa's corn and soybean crop for that growing season, and caused approximately $11 billion in damage, making it, by some measures, the costliest thunderstorm complex event in modern U.S. history. Generated entirely by the same downdraft and outflow mechanism described in this video's mechanism section, organized at the scale of an entire weather system rather than an isolated cell. The technological response to thunderstorm hazards has evolved substantially across each of the four mechanisms this video has covered. Doppler radar, now standard across the National Weather Service's nationwide network, can detect the rotational signatures associated with tornado-producing supercells, the reflectivity patterns associated with large hail, and increasingly the velocity signatures associated with damaging straight-line wind and microburst events, providing meteorologists with detection capability for wind hazards that didn't exist before Doppler radar's widespread deployment in the 1990s. Lightning detection technology has advanced dramatically through the deployment of the National Lightning Detection Network and, more recently, the geostationary lightning mapper aboard NOAA's GOES weather satellites, which can detect and map lightning activity across an entire storm system in real time from space, including the in-cloud and anvil lightning activity that produces the bolt from the blue hazard. This satellite-based lightning mapping represents one of the most significant recent advances in thunderstorm hazard monitoring because it provides direct visibility into the specific mechanism anvil cloud charge that produces lightning strikes furthest from a storm's visible core. Flash flood forecasting has similarly advanced through the integration of Doppler radar rainfall estimation with detailed terrain and watershed modeling, allowing the National Weather Service's flash flood guidance system to estimate for specific small watersheds how much additional rainfall would be required to produce flooding given current soil saturation and recent rainfall history, a forecasting capability that directly targets the training thunderstorm mechanism by modeling cumulative rainfall impact rather than treating each storm cell in isolation. The National Weather Service's impact-based warning system, rolled out experimentally in some regions over the past decade, represents a direct, if partial, response to the warning criteria gap this video's twist section identified rather than issuing a uniform severe thunderstorm warning, regardless of which specific mechanism is driving the danger. Impact-based warnings include tailored language describing the specific threat, considerable, or destructive tags for hail and wind. A thunderstorm is, statistically, the single most common form of severe weather most Americans will ever personally experience, more common than tornadoes, more common than hurricanes, more common than wildfires for the large majority of the country's population. Most thunderstorms pass without incident. Most lightning strikes the ground harmlessly, in open fields or on isolated trees, observed from a comfortable distance. This video opens a new chapter in this series, a chapter about the hazards Americans actually live with most frequently, rather than the rare or historical disasters this series has spent its first 29 videos exploring. Thunderstorms are the right place to start that chapter, precisely because familiarity is exactly what produces the kind of risk miscalibration this video has spent its time documenting. A hazard experienced dozens of times without incident breeds a justified general confidence that can, in the specific moments that matter, miss the mechanism that's actually present. Here's what I want to leave you with the next time you hear thunder. However distant, you are within range of the lightning that produced it. There is no safe distance at which thunder is audible, but lightning is not a risk, because sound and the electrical discharge that creates it travel from the same point. The 30-30 rule that lightning safety experts have promoted for decades remains the single most actionable piece of advice in this entire video. If the time between seeing lightning and hearing thunder is 30 seconds or less, the storm is close enough to strike you, and you should already be seeking shelter. Remain sheltered for 30 minutes after the last thunder you hear, because the anvil cloud lightning this video's mechanism section described can persist for that long after the visible storm has seemed to pass. That single number, 30 seconds, 30 minutes, is worth more than any amount of watching the radar app, because it doesn't depend on knowing whether the storm has been classified as severe. It works regardless of what warning category the Weather Service has or hasn't assigned, because it's based on the physics of how far you actually are from where lightning can reach, not on a wind speed or hail size threshold that was never designed to tell you that in the first place. Next week on ERTH, the tornado, a hazard we've covered once before in this series, but with a detail that changes everything about what "get to the basement" actually means, depending on which state you're standing in when the sirens go off. See you then.